Hi and welcome to another lesson about strings. Today's topic is first string instructions. Objectives of this lesson. We will study the string instructions STOS, LOAD-S, and MOVE-S. And we are going to see a lot of examples of those three instructions. In addition, we will learn about the direction flag and its significance with respect to those three instructions. Let's begin with STOS. STOS means store string. It has a few forms, and by the way, it doesn't have any arguments. So you just write down this instruction. You don't add any arguments to the instruction. So the few forms of this instruction. The first one is STOS B. B stands for byte. This instruction stores the value of AL into the address EDI, and then EDI is advanced by 1 byte. I want to emphasize that this data copy, is a data copy of size 1 byte, which means that we copy the value of AL into the memory location at EDI. And don't worry about what we see here in parentheses. I'm going to talk about it soon. The next form is STOS W. W stands for word. In this form, we store AX into the location EDI. And this time, this copy is of size 2 bytes. Right after this copy, EDI is advanced 2 bytes. The third form is STOS D, where D stands for DWORD. Here we copy EAX into the memory at location EDI, and this data copy is of size DWORD, or 4 bytes. Here EDI is advanced as expected 4 bytes. Let's look at a simple example. First we initialize AL to be the value 3B, and next we use the STOS B instruction to store the value AL into the location pointed by EDI. So we get this effect of storing 3B into the location where EDI were in. And immediately EDI was increased by 1. I want to show it again. First we move the value 3B into AL, and then we invoke STOS B, which stores the value 3B into the current location of EDI, and then it increases EDI immediately by 1. The direction flag. I remind you the discussion about the flags register. We have seen some flags before, but we haven't discussed the direction flag. The direction flag is not a status flag, which means that it doesn't change when things happen. It is more of a control flag. You have full control over this flag, and it changes the behavior of some instructions. As you can see in this table, it is bit number 10 inside the flags register. It is also known as DF, which means direction flag. The direction flag determines the direction for string instructions, which means that for direction flag equals 0, the pointers increase, and for direction flag equals 1, the pointers decrease. Remember when I said that EDI is advanced, for example, by 1 byte or 2 bytes or 4 bytes, the direction where EDI advances depends on the direction flag. If the direction flag is 0, the pointers increase, which means that EDI will increase. If the direction flag is 1, the pointers decrease, which means that EDI decreases. We have full control over the direction flag, and we have two different instructions to change it. The first one is CLD, which means clear direction. This instruction clears the direction flag, which means that it is changed to 0. The other instruction is std, which means set direction. It sets the direction flag, which means that it changes its value to 1. In your programs, df will usually be cleared, which means that in the usual way, df equals 0. If you don't do anything, then probably df equals 0. Let's look at an example where we change the direction flag and see the effects. Here we can see some code where first we move this value into EAX, and then we clear the direction flag and store a D word twice. Then we move another value into AX and then set the direction flag, followed by 2 STOSW instructions. I remind you that STOSD instruction is about storing one D word, which equals 4 bytes, but the STOSW instruction is about storing 2 bytes, which is one word. D stands for D word and W stands for word. So let's follow the code and see what happens. I assume here that EDI is set to some location in memory. EDI was set previously to this number somehow. We don't care how at this point. This is a picture of the memory, and we can see that EDI points to the first cell, which is in address 402000, which is a typical address. We also can see that the direction flag is currently 0. Let's begin. We move the value 1F into EAX. Next, we clear the direction flag. This is not going to have any effect because the direction flag is already 0. We do it just to be sure. Next, we store a D word to the location pointed by EDI, which is this location, which means that we are going to store a D word over those 4 cells. The D word that is going to be stored is the contents of EAX, which is currently 1F. As we can see, the value 1F was stored into those 4 bytes. As expected, it is stored in this order because of endianity. I remind you that the Intel processor is a little endian architecture. Therefore, the lowest significant byte is stored in the lowest address. Basically, this is just the reversed order of bytes compared to what you see here. Let's move on. We have another STOSD instruction, which should have a similar effect, just that this time we store the D word over these 4 bytes. And as expected, we get 1F000, and EDI has moved to this new location. It now points on this address. Next, we move this new value into AX, and we get that EAX equals 2255. And currently, we only care about AX because soon we are going to use those STOSW instructions, which only care about AX. They don't care about the total value of EAX. Next, we change the direction by using the set direction instruction, which means that now the direction flag is of value 1. It also means that now the direction is to the left and not to the right. Next, we invoke the STOSW instruction. This instruction is supposed to store AX, which is this value, into those 2 bytes, which are pointed by EDI. And as expected, we got those 2 bytes stored here. As usual, we got it in the reverse order because Intel x86 architecture is a little endian architecture. as we can see, EDI has moved to the left, or in some other words, it has decreased because the direction flag is currently 1. Next, we invoke another STOSW instruction, which is going to store the current value of AX into those two cells, those 2 bytes. And as expected, we got 5, and 2, which is the reversed order of bytes of the current value of AX. So this is how the direction flag works. Some notes about responsible use with the direction flag. The direction flag affects the behavior of some instructions. We've just seen the STOS family of instructions, but there are some other instructions that are affected by the value of the direction flag. Many subroutines and pieces of code assume implicitly that the direction flag is 0. You will see many times code that uses these kind of instructions, for example, STOS and some other string instructions, and those kind of instructions depend on the value of the direction flag. However, many times the direction flag will not be set or cleared in the beginning of the code, which means that those pieces of code assume implicitly some value of the direction flag. They assume that the direction flag is 0. Leaving the direction flag with the value 1 is equivalent for asking for trouble, so don't do this. If you decide to set the direction flag, make sure to clear it later. It is your responsibility to do it. If you change the direction flag to 1, expect some trouble. This is an important warning for you regarding the direction flag.